Okay, hello. So I want to just post a little video here on kind of the evaluation metric that we've been using for clustering because I just don't think I've been doing a really great job explaining it. So we're going to go through it. I'll try and make it pretty quick, but all right. So let's start. So one of the issues here, I think, kind of on the slides, is that we refer to this as inner cluster difference. You know, the difference between the clusters, and then within sum of squares. I guess we put between here, but then when we go down here, we actually don't refer to it as within, or I'm sorry, we don't refer to it as inner. We refer to it as between. Okay, so between. All right. So first thing I'd like to do, and I probably should have had this pulled up, but I want to take a look at this. I'm going to scroll this up. Oh my gosh. This stuff out of here. Get out of here. Uh-oh. We have to do a new one. All right. There we go. New whiteboard. All right. We're going to go rainbow ink. All right. So let's think about the principle behind this particular evaluation measure is actually sum of squares error. All right. That's really what it is. We're trying to, the entire Lloyd's algorithm is actually working just to minimize the amount of error represented by the centroids. All right. So let's think about this from kind of a the traditional example maybe that you're used to, which is, linear regression, right? So we have these linear, we're trying to fit a line between linear regression, right? And when we do sum of squares error, it's basically, the distance, sum of the squared distances between these points and the line, all right? So the summation of all these differences equals the kind of sum of squares error, mean squared, you take the average, mean squared error, right? Okay. So we got that. So I probably should have left that up. That's okay. So let's compare that to what clustering does. So again, this is a hyperdimensional space. So keep that in mind, but we're showing it in 2D. We have two clusters, one here, one here, right? And then we have a whole bunch of points. Yada, yada, yada. Yada, 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 yada. All right. And then the distance from these points, right, into the centroids is a version of error, right? It's the same measure. It's just there's not a line, right? So with regression, there's a line. All right. With the centroids, with clustering, there's clusters. Okay. So the distance from all these points to this centroid, and the distance from all these points to this centroid is the within squares error. So I call that within squares error. All right. Within squares error with my lovely rainbow pen. All right. Within squares error. All right. If we add these two things together, assuming we have two centroids, 1 and 2, if we add those together, that equals the total. Total within, you guys know how I am at spelling. Anyway, total within squares error. All right. So you can think of that as like the sum of squares error. That would be analogous to a regression model. That's explained. That's explained by the centroids. Okay. All right. So and then we have this between. All right. And so what between is whatever remaining error is not explained by the centroids. Basically, the distance between those, and we get to the between by calculating the total sum of squares error, right? We do the totes, all right? And so the total sum of squares error is the distance from every point from the global middle. Here's the global middle, all right? So it's not the mean, all right? But keep in mind, you think of this thing as a sphere, right? Is that there's this global space. In the middle of that space is the distance from each line from that global middle, okay? So you can think of it as, like the core of the Earth, right? The distance from every point to the core of the Earth, essentially, all right, is the total sum of squares error, okay? And so as we know what that is, we can subtract this total within and then that gives us this basically between. So we call it between, but it's really not between. It's kind of all the remaining variance that's not accounted for by the distance from the centroids. All right. Okay. So all of these things are a quantification of a reduction of this square's error kind of idea. So let me show you. I can do this. Everybody learns a different way, so we can do it in a little Excel spreadsheet if we want. These are our points. Let's look at it this way: 1 through 20. Okay, these are just those have no numerical value. They're just points. All right, so we have 20 points. Just think of it that way. All right. And then they're 1 through 20. All right. And then I guess they have some, pretending like they have some numerical value. But here, the global center, or the global middle, is going to be 10.5. Okay. So I'm going to use these as real numbers, but in hyperdimensional space, it would be the average of the distance between all of those features that you're trying to map. All right. So where that point locates in hyperdimensional space, and then the distance would be measured by Euclidean. All right. So we're doing this as if it's just addition and subtraction, but the way it's done in k-means and many other graphical based is the distance in n-dimensional space measured by Euclidean distance, right? How far away it is. Okay. All right. So the global center here is going to be 10.5, all right, which is just the middle point between this range of numbers 1 to 20. All right. So what we do here, all right, is we're just subtracting the distance, all right, and then I'm squaring it. Okay. So this is just a illustrative example. This is not how it would be done mathematically. It would use Euclidean distance, which is a bit different. All right, but we're just going to subtract the differences here, and then we're going to square them. All right, we sum that all up, right? This is the global center. So the sum of this is all of the distances, the sum of all the distances inside. So that's our total variance, all right, of our data set. Okay, and then say we had two centroids. We had two centroids, one at 5 and 15. All right, kind of at the midpoints of both of these potentially. All right, and then in order to find the distance from centroid 1, assuming that we just, mapping the first 10 onto that particular point, that's what this would be, right? And it's just squared differences, right? So here again, we're just subtracting 1 from 5 and squaring it so it's all in absolute terms, right? All right. And we're just adding that all up. And same here, it's going to be the same because they're the same exact numbers, right? They're just on different sides of the scale. So the distances are all going to be almost exactly the same. So we're going to see these are the sum of squared error, right, of both of the centroids. So this is within centroid 1 and within centroid 1, within centroid 2. They're the same. If we add those together, right, we sum these together, it's 170. That's right here, right? So that's our total within sum of squares, right? And then we know our total sum of squares, right? We did that. That's the distance from the global center of all of these. All right, and then we just, to get the total between, we just subtract the sum of the within from the total. And that's it. We get 495. Okay. So then if we want to understand the total amount of variance accounted for by our two centroids, by our two clusters, what we do is we take this between number, right, which again, remember, is basically the variance left over after we subtract it from our centroids, and we divide that by the total. Okay, and so in this example, that's 0.75. Okay, all right. So what will naturally happen is that while complexity will increase, all right, the sum of squares error. My little pen. I can move up here. All right, so as complexity increases, that means as k increases, right, sum of squares error will go down. Okay, that means the more clusters you put on the graph, the distance from those clusters, and you can think of this as within, if you want to do it, within sum of squares error will go down. All right, and variance explained will go up. All right. So the question you have to ask yourself, and this is what we're kind of talking about in this class, is this: we have this elbow right? So we know there's going to be a point of diminishing returns, okay? To where if we continue to add additional complexity, k goes up, variance explained will go up, right? Oops, sorry, that's not an up. Variance explained over here will go up, all right? We will have this kind of diminishing returns effect, okay? So we don't want to try and optimize that. We have to use our intuition about what makes sense. And that's why we do the elbow chart, right? And it kind of makes sense when you think about this as like a two-dimensional space, right? If, say, in a just terrible example, we just had like 2 points and we're trying to, and then, the clusters were just sitting on top of those points, right? So this would be where, the clusters explained 100% of the variance, right? Because the total variance inside, right? The total variance, the totes number from the global mean, and that would be the distance, say, to here, is going to be explained by the between distance, right? So you'd have 1 divided by 1, which would equal 100%, right? In this example, okay? So if the total between equals the total sum, for some reason it was so, clusters are so tight, essentially you just have 2 clusters, right? This would result in just a 1-to-1 ratio, okay? Anyway, that's an extreme example, but I'm just trying to explain that, hopefully in kind of just a extreme example, so you can understand the concepts there. Okay, so essentially what we're thinking about here, generally is kind of this reduction of sum of squares error. All right, but we never want to have like a perfect zero. If sum of squares error equals 0, what does that mean, right? Well, it essentially means, just like this example, it's the same thing, right? Is that there's a cluster for every dot, right? So the distance from a dot to a cluster is 0, right? And that would mean that we've overfit. So imagine we had, in some of the examples we had 300, 300 rows of data. That would mean we have 300 clusters, right? So you have 300 clusters on here, and you've perfectly explained it. Well, you haven't really explained anything. You've just memorized the data points. So you've overfit, right? When you get a sum of squares error that equals 0. All right, so the same thing if you get 100% variance explained. You just overfit. That means you have a 1-to-1 ratio between the total variance and the kind of the between. All right, so you're not really learning anything. So when we think about kind of explaining this, we have to look at it not only through the lens of variance explained, right, or sum of squares error, but also with this idea of what does it look like visually. So when we put it on the chart, okay, so that's true of of this week's, and all these explanations are here as well, so you can work through these now with, I think, better information, right? So we have to represent these things visually. Right? So that's why we're doing all this work here. And it might be, clearly we have 2 clusters here, but it might be that, adding the third one, which would increase the variance explained and reduce the sum of squares error, might be the way to do it. All right, so it might make more sense because these clear to be outliers, but maybe not, right? So much of what we see in clustering is a bit of human intuition about what makes sense, depending on what question you're asking. And evaluation of the clusters should be done through that lens as well. So you should take into account variance explained, but you should also take a look at what it is telling you graphically and see if it makes sense. And if you can use it, in a very simple way without increasing complexity, right? Then that's what you want to do. All right. So it's not always necessarily, and this is the nature of unsupervised machine learning, this perfect quantification of variance explained in terms of the things that we're trying to optimize. Last point, hopefully this helps too. For those of you that are versed in the just general variance kind of calculation, all right, this is the equation here, right? All right, this is the distance from every point to its mean, all right? And this should be squared, all right, all right, and then divided, right? And this is an unbiased data set, so you subtract 1 divided by this length of the data frame, length of the vector, right? Divided by the length, okay? So that's your standard squared error, right? Okay, so that's in R, That's just a variance calculation. Okay. All right. And so what we have here, all right, so this total variance, all right, is just the variance of the three variables that we're using summed together. Okay. So it's the variance of those three variables. I already printed it out down here at the bottom, so maybe a little bit of surprise kill there. But so in here, what we're doing is this is the between. These are features of our k-means object, right? So this is the between sum of squares error, all right? And then this is the total within sum of squares error, all right? So the total within the clusters and the total between divided by the length, subtracted by 1, just like the variance calculation, okay? And so if we compare these two, just the variance of the data points we're using and the variance of the objects generated in the k-means algorithm, they are the same, right? So I just wanted to show you that, maybe to ground that home. I mean, basically what we're doing here is trying to understand better the variance in terms of clusters as compared to the variance and errors in terms of a line like you might normally see in regression. Okay, that's it. I'm going to stop there, but I'm happy to answer more questions about this. Feel free to shoot me an email if need to, or of course stop by for office hours. Okay.